Hello friends. So, we were discussing about the finite element approximation for Euler-Bernoulli beam element, Euler-Bernoulli beams, and we discussed about the necessity to ensure continuity of not just the transverse displacement, but also its derivative across the inter-element boundaries. So, the primary variables are transverse displacement as well as the slope or the first derivative of the transverse displacement. Now, the interpolation function for that higher degree of smoothness is given by Hermite interpolation, and we have already discussed Hermite interpolation in our discussion of interpolation theory. But in this case we derived this from the first principles, from the basic requirement of the interpolation theory, that approximation has to be consistent, has to yield the primary variable at the nodes or the function specified function values at the nodes, and this is what we get as the interpolation functions, 4 interpolation functions for 4 primary variables in the element. So, 2 at each node, also referred to as the degrees of freedom. So, 2 degrees of freedom at each node. So, transverse displacement and slope, and collectively they are referred to as NV. So, that is shape function matrix or interpolation function matrix N, and the vector of nodal values of primary variables, that is referred to as V. So, properties of the cubic Hermitian interpolation polynomials functions. So, obviously n 1 when evaluated at x I, that is n 1 is 1, but its derivative when evaluated at x I is 0. Similarly, n 1 when evaluated at x j is 0 and its derivative also vanishes at x j. N 2 vanishes at n 1 at x I, but its derivative is unity, its slope of n 2 is unity at x I, and it vanishes at x j, and its derivative also vanishes at x j. N 3 vanishes at x I and its derivative also vanishes at x I, but it takes unit value at x j and its derivative is 0 at x j. Finally, N 4 has unit derivative at x j and the function value and its derivative at x I is 0, and it also evaluates to 0 at x j. So, this property is encapsulated in this plot of these interpolation functions. So, n 1 looks like this. So, it starts at 1 and the slope is of course 0, and it gradually goes to 0 at node j and with 0 slope. So, this is of course a cubic polynomial. N 3 is the complement of this. So, this is 1 minus n 1, if you compute 1 minus n 1 you will get n 3, and similarly for n 2 it starts with 0, but with unit slope. So, the tangent is angle is pi by 4 and it goes to 0 at n j with 0 slope. N 4 again it starts with 0 slope at n I at ith node, and it goes to have 0 value at node j with unit slope. So, finite elements based on these interpolation models, based on the use of these cubic Hermite shape functions, they ensure inter-element continuity of the function being approximated. So, that is the transverse displacement as well as its first derivative, that is dV by dx or theta, the slope of the deflected shape, and therefore, these elements are known as C1 continuous elements. C stands for continuity and 1 superscript 1 denotes the derivative order. So, the function with first order derivative is continuous. So, the function is of course continuous, its first order derivative is also continuous across the elements. So, continuous across elements. So, with this development, so finite element model is of course defined. So, we now we already have our weighting function, the weak form available with us. So, weak form of the weighted residual. So, W now we all that we do is replace W with respective interpolation functions n I, n 1, n 2, n 3, n 4, 4 weighting functions. So, one after the other. So, substituting finite element approximation for V hat into the weak form. So, that is n V, and choosing the element shape functions n I. So, I ranging from 1 to 4 as weighting functions. So, in sequence we use a weighting function as W as n 1, W as n 2, W as n 3, W as n 4, and these will be the 4 equations that we will have. So, these are the 4 equations that we have once we substitute it in the weak form. And because of these properties of these interpolation function, the boundary terms would obviously there will be of the 4 boundary terms, because each of these boundary terms is evaluated at 2 points, right, x is equal to 0 to L and x is equal to 0 and at x is equal to L, x is equal to 0 and at x is equal to L. So, there are 4 boundary points, boundary terms in this weak form. Now, because of this particular variation, you can see that the weighting function, they interpolation function, they will vanish for 3 of the 4 terms, and only one term would exist at that time at any point, right, and that is what happens here. So, this is what you get. So, this is for n I. So, this is the symmetric order, and then we transfer all the terms to the other side. So, this is the work done, I mean weighting function multiplied by external force, and this is first load boundary term, this is second boundary term. So, total x is equal to 0 and x is equal to L. So, out of these 4 terms only one term would exist at any point of time for any choice of n I, n 1, n 2, n 3, n 1 would exist only at x is equal to 0, n 2 would exist only for derivative of n 2 would exist at x is equal to 0, all other terms would vanish. N 3 would exist only at x is equal to L and all other 3 terms would vanish. Derivative of n 4 will exist only at x is equal to L, all other 3 terms would vanish. And that is what leads to, after substituting this and substituting for these interpolation function and evaluating this integral, eventually it is just a one dimensional integral in x. So, and substituting the limits, we get this particular element level equilibrium equations, which are very familiar. This is 12 E I by L cube, 6 E I by L square terms, and this is minus 12 E I by L cube, and this is 6 E I by L square again. So, these are standard stiffness coefficients for the fixed rigid moment transfer moment connections, and this is of course the integral of this for different choices. So, F L by 2, F L by 2 and F L square by 12, F L square minus F L square by 12. So, the moments, and these are the reaction secondary variables. So, shear force bending moment at node I, shear force bending moment at node J, that these derive from the boundary terms that we evaluate here. So, collectively we can refer to these equations as K E V E is equal to F E plus Q E. So, K E is the element stiffness matrix for Euler-Bernoulli beam element, whose ijth element is given by this expression, because V, the transverse displacement, is also based on linear combination of n i's. So, the shape functions. So, ijth element would involve product of second derivatives of ith shape function and jth shape functions, and of course, the flexural rigidity, which is quite often uniform, and for all ij varying from 1 to 4, and this is of course symmetric operator. So, that leads to symmetric stiffness matrix, as you can see, and this is of course by virtue of using Galerkin approach that this n I n j this happens. If weighting functions were chosen anything other than the interpolation functions, this symmetry would not have been there, but for structural mechanics problem this symmetry is not only desirable, it is essential to be consistent with the mechanics of the problem to satisfy the Maxwell-Betti reciprocal theorem. So, V E is the vector of nodal displacements, nodal primary variables. So, V I, theta I, V j, theta j. So, those are the variables. F I is the ith element of nodal equivalent force, nodal equivalent. So, the entire distributed load F is the distributed load over the entire element. So, that distributed load is being converted into the nodal loads. So, F I is the nodal equivalent of that distributed load F, and that is done by using again the work equivalent. It is the same amount of work. F I are the forces which will do the same amount of work in moving through displacement V I as would be done by distributed force F. So, that is the work equivalence of this nodal force. V I, M I, V j, M j, they are the shear force and bending moments at node I and j and are related to transverse displacement of the beam again by the boundary term expressions. So, V I is equal to proportional to third derivative of the transverse displacement at x I, V j is called proportional to third derivative of displacement at jth node, and M I proportional to second derivative of displacement at x I at ith node, and M j is proportional to second derivative of the transverse displacement at jth node. So, as I said, the elements of the load vector F E, they are the nodal work equivalent forces doing the same amount of work in moving through the nodal degrees of freedom as the work done by external force, external imposed loads in moving through the transverse displacement V hat. Now, V hat is a continuous function of x, external distributed load is continuous, it is distributed over the domain. So, whatever is the work done by the external force, we impose equality. So, the nodal equivalent force, nodal equivalent loads, they do the same amount of work in moving through that particular respective degree of freedom as the and we add it up all of them, and that will be the total work done by the force in moving through transverse displacement. So, once we have this, the element level equations, which is K E V E is equal to F E Q E plus F E plus Q E, these are the internal force secondary variables. So, these element level equations for each of the elements, again we can define, we can discretize the domain into several smaller elements, and for each element we can have, we will have similar kind of element level equations, and these element level equations would be assembled into global system of equations comprising of all the degrees of freedom of all the nodes in the structure of the finite element mesh, and that global system of equations would be accruing contributions from different elements, right. So, by accumulating contributions from all elements sharing a node and degree of freedom in the same manner as done in the case of assembly of C0 elements. The only difference being in case of C0 elements, particularly when we are looking at all the elements aligned in one line, one coordinate frame. So, there are only 1 degree of freedom at each node. So, there is only 1 degree of freedom to at each node and assemble, but For arbitrary orientation, there are 2 degrees of freedom, and it becomes similar kind of an exercise. So, the accumulation from all contribution from all elements at sharing a node and degrees of freedom happens in the same way as in done in the case of assembly of C0 elements. Just have to be consistent with the degrees of freedom and the common degrees of freedom and common nodes, and accumulate respective contributions from different elements. And then the essential boundary conditions of the problem can be incorporated as outlined in the context of C0 elements, that is again the stiff spring approach or penalty approach, and any imposed loads, point loads etc., at the problem in the problem, they can be defined by using these secondary variables. So, any discontinuity we place a node there, and then we take care of those discontinuous point loads, applied point loads or point moments, and cover them, include them in this Q term, QE term here, and then it will be taken up in the case of. So, this is the satisfying imposing the natural boundary condition. If there is any secondary variable that has been prescribed, we place a node at that particular point of point where the discretization, where the point loads are prescribed, and the secondary variables are defined appropriately and in the element level equations, and then it is taken up for the assembly. And after the assembly of the global system of equations, essential boundary conditions of the problem can be incorporated, and the resulting global system of equations properly constrained with respect to imposition of essential boundary conditions can then be solved for nodal degrees of freedom, or that is the unknown primary variables at the nodes of finite element mesh, and subsequently stress resultants or the secondary variables of the problem in different points of the domain can be computed from element level equilibrium equations during the post processing stage, because element level equilibrium equation we will have once we have this complete displacement, then we can compute the moment and shear force by the appropriate derivative. So, bending moment, I mean these are the displacement, we get this displacement function as a function of x in terms of interpolation of these primary variables, which we will get from the solution of global system of equations. And once we have this displacement within an element, we can find its derivative and second derivative for finding out the moment, and third derivative for finding out the shear force in the beam at different points, evaluate it at different points. So, that is what we call as post processing stage. So, finite element solution, the main processing stops with the computation of primary variables, solving for primary variables at the of the constrained global system of equations. After that, whatever any secondary results are required, more finer results are required, those are referred to as the post processing of finite element analysis. Now, as in the case of bar element, even the beam elements can be of any arbitrary orientation. For example, the framed structure, moment resistant frames. So, there are beams, columns and beams, and then there are inclined members also possible. So, there is no guarantee that all beams in a structure would be at the same orientation. For example, the skeletal structure, framed structure, or the staging of elevated water tanks, framed staging of the elevated water tanks, you can see beams interconnecting each other and at different elevation, at different orientation. So, we can do the same thing with the similar operation as in the case of arbitrary orientation, and Of course, transverse deformation. So, the beam element, Euler-Bernoulli beam element can only deal with transverse bending. So, axial deformation, they will have to be they are accounted for by using the truss element. So, beam elements of C1 continuity, they can be combined with truss or bar elements of C0 continuity for finite element modeling of the framed structures. So, in this particular stiffness matrix that we computed for the beam element, Euler-Bernoulli beam element, we will have 2 more rows and columns here corresponding to ui and uj, and respective elements would be, they would be decoupled from these flexural degrees of freedom, and there would be appropriate ae by l, ae by l, ae by l, minus ae by l off diagonal terms in the respective rows and columns positions of this matrix, stiffness matrix. So, that becomes the element level stiffness matrix for the frame element. So, combining C0 element and C1 element, C0 bar element and C1 Euler-Bernoulli element, we can get a frame element, and that can be used for modeling of framed structure with elements oriented in different direction. Now, in the same way as we did for the case of truss problem, these need to be transferred, these are the local frames of reference x bar, y bar. So, these degrees of freedom, the equations are derived in terms of x bar, y bar frame of reference for each element, and these equations need to be transformed to x y frame of reference, that is global common frame of reference, before the element level equations are assembled into global system of equations. And once that is done, then of course, the boundary conditions would be imposed, and equilibrium equations in local coordinate system are transformed to a global coordinate frame before assembly to build global model for entire structural system. And once this global structural system model is ready, analytical model, I mean simultaneous equations, then we impose the essential boundary conditions of the problem wherever there are constraints on the primary variable, and remaining system of equations is then solved for remaining unknowns of the problem, and then subsequently the again it going back to element individual element level, we can find out the stress resultants, bending moment and shear force at any point in any element of the structure, and that is how it works. So, that completes our discussion of C1 continuous elements. Now, C1 continuous elements, as I have been emphasizing, it ensures a higher degree of continuity, not just the function unknown basic variable unknown function of the differential equation, but also its derivative is required to be continuous across the element boundaries. Now, this is possible, I mean derivative, the slope is same as, or the section rotations are same as the slope, that is the fallout of natural consequence of Euler-Bernoulli hypothesis. The section rotation, plane section remain plane, but they can rotate after the bending. So, they may rotate after bending. So, this rotation of the plane is same as the slope of the deflected shape. So, that is a fallout of direct consequence of Euler-Bernoulli hypothesis, and that happens because of neglecting the shear deformations. It is pure flexure, right. So, if there are shear deformations present, which is the case in case the beam depth is much larger than width and not very small in comparison with the length. So, the deep beams, so to say. So, for deep beams, shear deformations are not negligible, you cannot completely ignore them. They may not be as large as flexural deformation, flexural component of the deformation, but they are not negligible either. So, in that case the section rotation is not really same as the slope of the deflected shape, because the deflection, transverse deflection is not just contributed by flexure, it is also contributed by the shear deformation. So, one to one relationship is lost. So, in that case what the model, finite element model, or the that we need to look at here is decoupling the two fields. So, the slope or the deflected shape of the transverse deflection and the slope of the transverse deflection, they are different, they are treated differently. So, they are taken as independent variables. So, they are interpolated separately. So, in that case there is no need for the interpolation for transverse displacement to ensure continuity of the first order derivative, because slope is entirely different, it is being interpolated independently, which it will be independent in case there are significant shear deformations. So, they are interpolated independently, and then the beam problem can be modeled as using C0 elements. The transverse displacement is interpolated independently, and the slope is interpolated independently at the two nodes. So, two nodes, I mean both of them are C0 continuous, I mean each of them are maintain their own interpolation function, and we work accordingly, and differential equation, there will be two differential equations, two sets of differential coupled set of differential equations, second order each. So, second order each, so we will again have first order highest order derivative in the weak form. So, C0 continuous element will do the job. So, C0 continuous elements can be used for approximation of those shear flexible beams. So, to say other theories are also known by the name of Timoshenko beam theory and such, and it is possible to derive beam equations by using just C0 model. But the problem becomes that is where the consistency requirement of finite element equations come into picture. This is fine as long as the deep beam being modeled is deep and there are significant shear deformation. But if this model is used for modeling thin beams, I mean where Euler-Bernoulli hypothesis works beautifully, the shear deformations are negligible. In that case there would be inconsistency if we use the same order of interpolation for displacement and the slope, because the mechanics of the problem require that the slope has to be like the first derivative of the transverse displacement, and if I use the first degree approximation, first degree interpolation for both the slope and the transverse displacement, then there is mutual inconsistency, and that leads to locking problem, that leads to very absurd results. The solution here is to have consistent interpolation. So, the displacements have to be interpolated at 1 degree higher than the slope interpolation, and once we do that all the problems are sorted out, and this consistent interpolation leads to acceptable, I mean very good results, actually consistent with what is observed experimentally. So, that completes our discussion on one dimensional finite elements. We will start with discussion of continuum finite elements, that is 2 dimensional and 3 dimensional continuum problems, and we will see how that is done. Again the basic process remains the same, the only thing that needs to be looked at is the what kind of elements are used and how the interpolation model, how the interpolation functions are developed. Rest of the things is exactly identical, it is very mechanical and very automated process. Thank you.